Good afternoon. Most of my lectures on the YouTube are at a more advanced level than this. This is high school. Okay, it could be at any level of high school. I'm going to talk about physical science. It's not really physical science, it's introductory chemistry. And it can be used anything from actually, I say 7th through 10th, 5th through 12th in fact. And even some people at college level could do with this knowledge, right? So what I do is I simplify things, take all the essentials, can all this IB stuff that confuses people, and literally sort out the wood for the trees for you. I will start at the very beginning. So we're discussing whatever is, now I don't need this up here anymore. Some people use the phrase properties of matter. Okay, I don't like it, but let's call it that. What is matter? It's the stuff of the world. We're going to lead up to the idea of elements, by the way, and how they combine to make all the things in the world. You'll find that the world is much simpler than you think. So matter, whatever it is, comes, depending on the temperature, in either solid form, liquid, or gas. Think water. It's steam when it's a gas, that's hot. It's liquid when it's at room temperature, and it's solid below 0 degrees centigrade, okay? So these things depend on the temperature. Actually, it also has something to do with pressure in there, but I'm skipping that. For now, at constant pressure, whatever that means, we'll talk about later. Matter comes in a solid, liquid, or a gas state. Some people say, what about a plasma? Forget that. We don't see any plasmas here on Earth unless you're in a lab. Now, I should add something extra with hindsight. We can have things which are metals, metals and non-metals. Example of a metal, iron, silver, copper. Example of a non-metal, anything else. In actual fact, well, let's leave that aside. So next, what can happen to substances? We use the word substance as well. Some people like to say anything that has volume, that takes up space and has mass, is going to be matter. Well, let's say that. However, mass is a very difficult thing to talk about. There are two different kinds of mass, although they are related. One is the one that responds to gravity, and the other one is the one that responds to if you try to kick it. You try to kick a soccer ball, that's fine. You try to kick a big rock that size, it'll hurt your foot. Inertial mass, gravitational mass. Okay, metals and non-metals. Now, there can be changes within substances. You can go from a solid to a liquid or a liquid to a gas. That's a physical change. There is no change in the substance. We can retrace our steps. If we melt ice, we can also freeze water to get ice. Ice and water are the same thing, the same in essence. We can also make steam out of either of them if we heated them up a little bit higher. But if we allow iron to rust, okay, we can't get back to iron if it all rusts away. it becomes iron oxide. We can't get back to iron unless we go through a chemical change. This is a chemical process to retrieve the iron. You could actually smelt the iron, heat it up really high. This is a chemical change. And roughly speaking, I'm saying in a physical change you get no new substance. In a chemical change you get a new substance. But wait a minute, what's the difference between water and ice? Are they new substances? Sure they are. I mean chemically new in nature, right? With a new chemical formula. When we learn formula, you'll see that that's the case. So, this is the essence of physical chemistry or physical science. Now, matter has mass. Matter has a related quantity. If I take the two things that I know about matter and relate them into a ratio, we can talk about the mass of a unit of volume, and I have a whole lesson on this. Somewhere on the YouTube, I have density, where I talk about Archimedes and all that physical stuff. So that's basically the beginning, and now launching into the chemistry. Now I only get 28 minutes for this stuff. Windows 10 plays games with all its users, and one of the games it plays is it stops me putting anything more than a certain amount of bytes on my computer, so I can only make a 28-hour video. Windows 7 doesn't do that, and Windows 10 takes your privacy a lot more so than does Windows 10. Another one that takes your privacy is the iPhone. Of course, Google cleans up. So the next thing. When we have a chemical change, we will go from one kind of compound to another. Chemical change. Now, I have not said what a compound is yet, but you know already some of them. You know carbon dioxide. You know water, H2O. Why they are CO2 and H2O will become evident in a while. Chemical change, compounds. But what do we have? In essence, in nature, we only have three different kinds of substances. Now, an element, whatever it is, in a minute, is a pure substance. A pure substance that cannot be broken down further by chemical means. Emphasize chemical, the chemical process. A chemical means is something that involves a chemical reaction. An example of a chemical reaction is the process of rusting. Another example of a chemical reaction is, let's think, an acid when it corrodes something. Throwing Alka-Seltzer into water creates a chemical reaction. Many things involve chemical reactions. All right? Compounds. Let's change this. Okay, so we won't say most of the world. We have two or more elements, whatever elements are, those pure substances chemically combined. Then we can have a compound. Two examples are water and carbon dioxide. Two examples common of elements would be iron or oxygen. Most of the elements will turn out to be metals actually, but ones that do the jobs that we need them to do will be non-metals. Two or more elements chemically combined would be, for example, water has hydrogen and oxygen in it. Carbon dioxide now we take iron and oxygen, we let iron rust in the air. It goes to that brown substance that coats the iron, and eventually you'll get all of this stuff, rust. Rust is iron oxide. It's the two elements, oxygen and iron, chemically fused, combined. Now we can also have a mixture. The other thing is where there are no chemical combinations of the substances, they're just mixed together. For example, you could throw stones into water. You've just mixed up stones and water. You could make a more homogeneous mixture by throwing salt into water. Salt is a compound. Now there are many salts, but one salt common is sodium chloride, NaCl. Sodium and chlorine combined, and a solution could be seawater, salt water. That's a solution. It's a mixture. The water and the salt do not chemically combine, but they make a more homogeneous mixture than stones or sand in water. Another example of a mixture could be two solids. We could take sulfur and iron dust, put them together. Now the whole thing about this would be, if we took sulfur, which is a yellow powder, doesn't react to a magnet, and we took iron powder and mixed the stuff up together, it would be kind of a yellowy brown colour. I could separate those things by bringing a magnet and pulling up the iron filings. I can also separate solutions. If I took salt water and I boiled off all the water, you would see the salt left in the bottom of the container. You could separate it by physical means, so we can separate physically. For compounds, you can only separate the elements by chemical means. For mixtures, you can separate them by physical means. That means heating, straining, using a magnet, all sorts of things like that. Okay? So now let's look closely at elements on their own. Now for this, unfortunately, I'm not equipped. Oh, I am. Now the ancient Greeks said that the whole world is composed of 4 elements. Well, in a way they were on the right track. Earth, water, fire and wind, right? So that's where the word elements comes from. But during the 19th century, it was realized that all the matter in the world, everything, look down at your floor, look up at the ceiling, look at the walls, look at the glass, look at your body, everything in the world, walk outside, walk down the street, all your food, everything is composed of a combination, a compound or mixture I use the word universe because it's not only true in the world. Elements, okay. Everything in the world is composed of a compound or a mixture of two or more elements, and I keep using the same examples. Carbon dioxide, water, table salt, rust I gave you as an example. What else will I put down there? Now then, these are compounds, and sometimes elements exist. Well, you get oxygen and nitrogen in the air, but in other, well, you could get carbon, is the black powder on burnt toast, okay? It's also a diamond. Graphite in your pencil, some pencils. What else exists as an element? Many things. Sulfur, I guess. That'll do for now, we get the picture. Now the question is, how many elements are there? Well, a fellow called Mendeleev in around the middle of the 19th century started listing them. He found patterns in the way that they occur in nature. And there were a lot of gaps in his chart, which is called the periodic table of the elements. It's an array of where we put all the elements for convenience. But gradually that whole gap, all those gaps got filled in. And it is now known that there are 92 naturally occurring elements. Now to confuse kids, if you open your textbook, you'll probably see it going up to 103 and 104, ending with Lawrencium sometimes, or even more. But those elements do not exist in nature. The first and the lightest known element in nature is hydrogen. So we'll give hydrogen the symbol H. That's number 1. So we say H1. Okay? We're going to call this the atomic number. But we know nothing about atoms yet. Right? In the middle of the 19th century, it wasn't appreciated what atoms were. That's a 20th century concept. So hydrogen is number 1. And the last one is uranium, number 92. Uranium is atomic number 92. It's last on the periodic table. The periodic table is the chart of the elements. So now we will look roughly at the periodic table. If you have one at home, it's great. I don't have one. I'm going to list the elements, first of all, in a row, as far as I can remember. I wonder if boron is that symbol. No, it's boron. So these are the first 6 elements. And then if we continue on, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So we give them symbols and numbers. Now I don't know if that's the correct symbol for fluorine. Yeah, it is. Okay, neon. Now it could be Si is silicon, yeah. P is phosphorus. Now, when we're here, we're going to notice something very weird. We're going to notice that magic number 10 is 2 plus 8. We're going to notice that this one is 2 plus 8 plus 8. There's something special about the number 8 when we go to study the elements, okay? Now, number 7 here is one less than 8, right? No, I'm looking for something else. Let's not deal with that just yet. Anyway, there's a special number 8, and when we look at chemical compounds, it will come into play. Now, okay, so when we have the elements sorted out like this, all in a row, and we go all the way up to uranium-92, most of them will turn out to be metals. Once we hit aluminium-12, they start becoming more metallic, and then when we get down towards these numbers, they're all metals, right? The non-metals are up there in a corner on a chart known as Mendeleev's periodic table. So today I'm just going to talk a little bit about the periodic table, and I wish you had one. If you're at home, go and get a picture of the periodic table up on the computer, okay? Or better still, get a paper one or a blank one and make your own. So I have it off by memory because I learned it when I was at school. I guess kids don't do that nowadays. Alright, so these are the elements listed in order, and I want to notice the symbol H for hydrogen, He for helium. So there's always a first, sometimes a second letter. The first letter for hydrogen is just a H, but since we have two elements sounding, beginning with a H, we have to put an E in for the next one, right? Lithium. Now I don't know if there's any element with an L. I'm not sure. How about that? Lithium is a case where you just have lithium Li. Anyway, beryllium Be, boron is just a B, because Bo might be something else, not sure. Okay, C for carbon, number 6, this is a special one. N for nitrogen, oxygen, number 8, try and remember this number. Fluorine, 9. Neon, magic number, 2 plus 8. Sodium, it's got an extra thing beyond the magic number, has a reason for being there. Aluminium, number 12, Al. Silicon, Si. Phosphorus, 14, P. Sulfur, 15, S. Chlorine is a poisonous green gas. Argon, actually let's say something about them. Hydrogen is a gas at room temperature, so is helium. Lithium is a very volatile metal. Beryllium, it's another metal. Boron, I think it's a non-metal, I'm not sure. Carbon is a non-metal. Nitrogen is a gas at room temperature, and so is oxygen. Fluorine is a poisonous liquid. Neon is a gas at room temperature. It's called a noble gas, actually. Sodium is a volatile metal. Aluminium is a stable, light metal. Silicon is in between being a metal and a non-metal. It's more like a non-metal. Phosphorus, a dangerous metal. Sulfur, a harmless yellow powder until you do things with it. Chlorine, a green gas. It will kill you if you breathe it in. Argon has a special situation just like neon. Those two are cousins. Here are two other cousins. Sodium and lithium. They are cousins. They're cousins for a special reason. They're kind of odd numbers, and that's the reason they're cousins. Okay? So we'll have a closer look at the periodic table, and we'll call it a day for our first class, then we move on to the next one. You'll find that this stuff is very simple. You see him in Frankie, I'm sorry. Now, the periodic table is organized in columns. And the first column is called the alkali metals because they make things called alkalis, which will come in later, except for hydrogen. Hydrogen is only in there because it has a certain structure that's similar to these guys, but these all have the same properties. And that was noted by Mendeleev. Now the next column in, magnesium, I forget now. No, I put it out of order. Because lithium, sodium, potassium, that's why. There should be a K in here. Potassium, all right? Is RBA and RA. These are called the alkaline earth metals. And they're similar in properties altogether. Not quite the same as these ones, slightly different properties, but enough for Mendeleev to put them all in the same column. We then have a whole lot of average elements in here, transition elements. And then we come over to some more groups here. Let's get that right. Now, at the very end of the periodic table, we have the noble gases. Gosh, I'm forgetting this stuff. Oh yeah, helium, neon. Now this shouldn't be here. Oh, this is radium. So, the noble gases are special insofar as, first of all, they're all gases, and second of all, they're also called the inert gases. They do not react with any other elements. They make no compounds. These ones are very likely to make compounds with anything, and these ones don't do anything. And the periodic table is all organized in those columns so that it looks like this. Non-metals are up here. And all the rest are metals except for hydrogen. So have a look around the periodic table and you'll see different colors or something special. Roughly speaking, this is the way around the periodic table. The alkali metals, the alkaline earth metals, the transition elements, the oxygen group, and so on and so forth. The inert gases or noble gases are at the end, and we'll build on this information next time. So this is easy stuff, right? It's all logical. Wait till you learn how to name compounds, write formula, and write the equations for chemical reactions. Then you'll feel like you understand a lot of chemistry, and you will. Okay, so we're not doing the lab stuff in here. This is the theory behind it.